So hello everyone, and we are in the second part of deriving our gradient in spherical polar coordinates, and this is part 2. So in part first, what we have done is that we have expressed our unit vectors er, e phi and e theta in terms of ex, ey, ez that are unit vectors in Cartesian coordinates. And let me remind you what we are trying to achieve here. So we have our gradient operator in f. Let me write a little bit bigger. So we have our gradient del f x y z is equal to df over dx ex plus df over dy ey plus df over dz ez. Okay, so what we were trying to do is that we want to derive an expression for f theta phi. So this would contain some er, e theta and e phi, right? There will be some terms here. So what we were trying to do is that we were trying to express my ex in terms of, so let me write in terms of er, e theta and e phi, all the unit vectors ex, ey, ez. So once we do that, we can actually plug it in here, right? And second, and so this was our task 1. This was our task 1. The task 2 was to write df by dr, df by d theta, or sorry, the other way, df by dx, df by dy and df by dz in terms of df by dr, df by d theta and df by d phi. So therefore we will plug this, we will again plug this expressions for del f by del x, del f by del y and del f by del z here in this expression in place of this, and the expressions for this in terms of er, e theta and e phi at those places, and finally we will get our expressions, the entire expression in terms of er, e theta, e phi and del f by del r, del f by del theta and del f by del phi. So that's our goal. We want to express everything in terms of spherical polar coordinates by replacing the Cartesian unit vectors and the Cartesian derivatives by polar derivatives and polar unit vectors. Okay, that was our goal. So we are in task 1. So let me actually copy this down, what we have achieved yesterday or in the last lecture. So let me copy these whole equations, copy. So that is what we have, right? Okay, this is what we have derived. So let me write this in matrix form, because this is er, e theta and e phi in terms of ex, ey, ez. I want the reverse relation, I want the inverse relation, right? So let me express this in matrix form. So if you write this in matrix form, you will have er, e theta, e phi is equal to matrix sin theta cos phi, sin theta sin phi, cos theta cos phi, cos theta sin phi, and minus of sin theta. So this is minus here, let me minus of sin theta, and here we have minus sin phi, cos phi 0, and there we have ex, ey, ez, right? All we have done is expressing these three quantities, these three equations in matrix form. So the first equation says sin theta sin cos phi, sin theta cos phi, sine theta sine phi, sine theta sine phi, cos phi, cos theta, sorry, in terms of ex, ey and ez, right? So similarly the other two equations will give you the other two equations. So once we have that, you realize, so let me write this, you realize that we are going from one right-handed coordinate system, RHCS, right-handed coordinate system, to another right-handed orthogonal coordinate system, Here I am talking about Ex, Ey, Ez, to Er, E theta and E phi. So the transfer matrix is an orthogonal matrix. You can easily check that. What do I mean by orthogonal matrix? That this matrix Q, let me represent this by this matrix. Let me represent this matrix by matrix Q. So the Q matrix will satisfy Q transpose is equal to Q transpose Q is equal to identity. What it means is that the Q transpose, or simply the Q inverse, is nothing but Q transpose. That's simply the property of orthogonal matrices. So this right here, this matrix that we have here, this one is an orthogonal matrix. You can easily check this, and I would urge you to please check this. So this is a homework. Homework is to check Q transpose Q is equal to Q transpose is identity. Please do this exercise. Straightforward exercise. Please do this. Please verify this. Okay. So once we have that, so we have this relation Ex, Ey, sorry, we have Er, E theta, E phi is equal to Q times Ex, Ey, Ez. Therefore, it implies that, what does it imply? It implies that Ex, Ey, Ez is equal to Q inverse Er, E theta, E phi. Right? But as we have pointed out that Q inverse is Q transpose. So we have, this is Q inverse. So we have Ex, Ey, Ez is equal to Q transpose Er, E theta, E phi. So just take the transpose of this matrix that we have, and by doing that you will get, so what I'm saying is to take the transpose of this matrix, transpose of this matrix. So let me copy this matrix. Let me copy this matrix for you. Copy. Here is my matrix, just for your reference here. Sorry, extremely sorry. This is my matrix, right? So I need to take the transpose of this matrix. So the transpose of this matrix is sine theta cos phi. I'm running out of place here. Cos theta cos phi. So let me actually delete this. Sorry. But please take the transpose. You know what a transpose is, right? You make every column into a vector, and you make every vector into a you make every row into a column, and that's it, right? So we have sine theta cos phi, cos theta cos phi. Then we have minus of sine phi. Just take the transpose of this guy. So this will become my first row. Then the other guy would give me sine theta sine phi, cos theta sine phi, cos phi. Then will give me cos theta minus sine theta and 0. So just take the transpose and you will get this. Easy exercise. Okay. So now I have almost achieved my result. I have now expressed my Cartesian unit vectors in terms of my spherical polar unit vectors. So let me write in an equation form. So you have Ex is equal to sine theta cos phi Er plus cos theta cos phi E theta plus sine theta E phi, right? Sorry, sine phi E phi, correct? Is it correct or wrong? Is there a minus sign here? Let me check. Yes, there is a minus sign. So I forgot the minus sign. There is a minus sign here. So this will give me a minus sine phi. Okay. And similarly Ey would give me this guy multiplied by this. So we have sine theta sine phi Er plus cos theta sine phi E theta plus cos phi E phi. And third and last Ez would be simply cos theta Er minus sine theta E theta plus 0 E phi, right? This is my final expression for, so this is my final expression for let me make this box. Okay, so yeah, this is my final expression for expressing my Cartesian unit vectors in terms of spherical polar unit vectors. So my task 1 is done. Task 1 is complete. Task 1 is complete, right? Now let me come to task 2. So task 2 was to write df by dr first in terms of df by dx, df by dy and df by dz, right? And then to invert those relation. So first let's write df by dr. So df by dr, as we know that f is a function of x, y, and as we know that f is a function of x, y, and z, so this would be used, so that would be using chain rule. It would be df by dx, dx by dr plus df by dy, dy by dr plus dy by dz, dz by dr. And similarly theta would be x, delta x by delta theta, delta y delta y by delta theta, delta z, delta z by delta theta, and finally phi, del f by del y by del phi, del f by del z by del phi. And you can, and you know the relations, right? X is equal to r sine theta cos phi, y is equal to r sine theta sine phi, and z is equal to r cos theta. And therefore you can compute these relations, this one which I am marking in yellow. This can be easily computed, right? For example, so let me compute the first one. Del f by del r is equal to del f by del x, del f by del r. In place of r, in place of x, we have r cos theta. So basically the r derivative of this guy. So basically the r derivative of this guy. Now r derivative would simply be will act on r, not on theta and phi, and therefore it will give me sine theta cos phi, plus we have df by dy, and r derivative, and r derivative on y would give me sine theta sine phi. Similarly, plus we have del f over del z, and we have r derivative would act on this guy, and it will just give me cosine of theta. Sorry, yes, cosine of theta. Okay. And similarly, you have df over d theta, which is delta x. So let me write those terms first. And now I need to write the derivative terms. So my theta derivative, so here is my x, del x by del theta. So the theta derivative would act on sine theta and give me a cos theta. So this is r cos theta cos phi. Similarly, it will act on y, and it will give me r. It will give me r again cos theta sine phi, and from the z it will give me minus of sine theta, because derivative of cosine theta is equal to minus sine theta, right? Now lastly we have del f over delta phi, which is equal to del f over delta x plus del f over delta y plus delta phi del f over delta z, and these terms. So the first term, again you have to take the phi derivative of this guy. It will act on cosine of phi, so it will give me r sine theta sine phi with a minus sign, right? And similarly it will act on this guy. It will give me r sine theta cos phi, and there is no phi here, so it will just give me 0. Okay, so we have obtained this expression. So let me box this relation, because we will need this relation in our next upcoming videos. Okay. So I think in this video, let me finish here. So let me summarize what we have done. So we were talking about this gradient operator in spherical polar coordinates, right? So in the previous video we have obtained the relation between the Cartesian unit vectors and spherical pole and the unit vectors of spherical polar coordinates er, e theta and e phi. So but we wanted to reverse or inverse this relation to get my ex, ey, ez in terms of er, e theta and e phi, right? So therefore we inverted those relation, right? We inverted those relation by realizing that the transfer matrix is orthogonal matrix, right? I told you to check this, please do this. This is orthogonal matrix, and what does it mean? By the definition of orthogonal matrix is that q transpose or q transpose q is identity. So the q inverse or the inverse, that the matrix which takes you from the matrix that actually takes you from ex, ey, ez is the inverse of the initial matrix, right? And the inverse matrix is nothing but a transpose of the original matrix, because the matrix is an orthogonal matrix. So we figured out the relations which is given in this box, and so that is where our task 1 was complete, right? So the other task was to figure out del f by del r, del theta by del f by del theta, and del f by del phi in terms of df by dx, df by dy, and df by dz. So we have achieved that. So we have achieved that too, right? And the next task would be to use this relation and to find df by dx in terms of del f by del r, del f by delta theta, and del f by delta phi in terms of this. Similarly for this guy, and similarly for this guy. So I want to express those in terms of this, and once we have that, then we can just plug this in, which is ex. So let me copy this actually. Once we have that, then we can simply copy this and put it in our expression to get the final expression. So what I am saying here is that this guy, sorry, let me actually write it. Ex so we have this unit vectors in terms of er, e theta, e phi, and finally we have this in terms of del f by del r, del f by delta theta, and delta f by delta phi. So once we plug this, then we will have our entire expression for gradient in spherical polar coordinates. So that is what we are heading towards, and I probably in the next video it will be complete. Okay, so with that I would leave you. So with that I will leave you. So I hope to see you in my next video, where we will try to finish this discussion on gradient in spherical polar coordinate system. Okay, so see you.